Okay, here is a page in OneNote you have access to. This page, the name is called up here, Infectious Disease Modeling with Excel. And it's based on a web page that I copied. You can find the address here if you want to find the original web page. Now I'll go through this step by step and explain to you the different parts. This author implements a disease model in Python, and you will be implementing in Excel. So let me pick out the high points here of his model. First, you see this graph here. You have time in days, and then here you have population. All right, looks like you're starting with a population of 5,000. And here you see the different categories: susceptible, exposed, infected, critical, recovered, and dead. Now, previously you saw SEIR, susceptible, infected, and recovered. Now he has added 3 more categories: exposed, critical, and dead. So you see that you can add complication to your model. So we'll see how to do that. One thing I should point out is that his notation is slightly different from the notation I used. You have to get used to this. Different authors use different notation, so you have to be careful. For instance, his beta means something different from the beta that we used previously. Well, we'll see that shortly. All right, here's some other graphs that you have the reproduction number over time. And then this is called case fatality rate, and this is deaths per day. So you can plot things like this. We'll probably be focusing more on this graph. We might do a deaths per day graph. All right? So let's go down and see this. So here you have a all right, so he talks about having talked about SEIR, and you already have an introduction to SEIR. And here is going to introduce some extensions. And as I said, here we have a dead state for individuals that pass away from the disease, exposed state for individuals that have contracted the disease but are not yet infectious, okay, and time-dependent reproduction number values, okay, that will allow us to model quarantines and lockdowns, etc. Okay. As you know, if you have a quarantine, then people are less likely to spread the disease, or if you have a lockdown, so that will change the infection rate. It's by changing the number of contacts. Then we have resource and age-dependent fatality rates. So since we're introducing a dead state, we'll have a rate of fatality. All right. Now, when you program your model, you will have to use variables. Some of these are similar to what we had. N is total population. S is number of people susceptible on day T. I, number infected. R, number recovered. Okay. And this beta is expected amount of people an infected person infects per day. Now that's slightly different from the beta that we've seen before. If you look at our previous model, which I have here, here we had beta defined this way. This was the rate of infections from, this should be coming, yeah, beta SI. Okay, so if you consider a single infectious person, that would be 1. So in fact, beta S is the number of infections produced by a single infectious person. Okay, so his beta is slightly different from ours, and you'll see how that works out in the equations. In fact, this is not quite accurate here, what he's saying here. This is the expected number of people an infected person infects per day, and this is given that everyone is susceptible. So this is actually given that all are susceptible. And you'll see that works out shortly. Okay. These are the number of days that an infected person has and can spread the disease. That's R little d. A gamma is the proportion of infected recovering per day. So that's a gamma. I think that's the same as ours. And R naught is the total number of people an infected person infects. So he writes this as beta over gamma. So you remember that our formula for R0 is a little bit different. All right. So he writes some basic equations based on this. Now, he has derivatives here. He says the time derivative of susceptible is minus beta times I times S over N. Now, we didn't have the S over N here. The reason why he has S over N here is that this is the proportion of susceptible. Okay, so actually what we have is beta. Beta is the number of infectious contacts. That's how we should say it. And S over N are that's the proportion of people who are contacted by an infectious contact that can get infected. So this is the proportion of infectables in the population. Okay, so as I said, slightly different notation, but the idea is the same. All right, going back to this derivative, ds dt. Okay, now you may have seen this basic formula for derivative. ds dt is the same thing as s of t plus delta t minus s of t divided by delta t. All right. Now, suppose we consider the case where delta t equals 1. Okay. And we'll, instead of t, we'll use n. So let n equal denote the days. So instead of t, we're using n. Instead of delta t, we have 1. So this becomes s of n plus 1 minus s of n. Okay, so we can replace this ds dt by s of n plus 1 minus s of n. And that should look a little bit more familiar. Now, I think previously I used s of n minus s of n minus 1, but the principle is the same. Similarly, the I dt is going to be I of n plus 1 minus I of n. Okay. Again, I used I of n minus I of n minus 1, but the principle is the same. And then here we have R of n plus 1 minus R of n. All right, now when we did these equations, we put the s of n on the other side. Okay. If you look at that and you look back at the equations that we have, this in fact is exactly the same as the equations we had before. All right. So far we're on familiar ground. All right. And now he's going to motivate the representation. S, that's the S represents, the symbol S represents the population of susceptibles. So here we have rate times probability times population. Now, the way he interprets these quantities, you need to read the paragraph and see how he's interpreting this. I think the best way is to look at this example. If we look at transition from susceptible to infected with beta equals 2. Now remember what beta means. Beta actually means the number of potentially infectious contacts per infected person. So let's write that here again. Beta equals the number of potentially infectious contacts per person, per infected. Okay. So here we have a total population of 100, and there are 10 infected and 90 susceptible. So here when he says population, he says the transition applies to 20 individuals. And this when he says population here, this is the population of potentially infected. Right? Because if you have 10 infected and beta equals 2, you have 20 infectious contacts. So when he says population here, that's what he means. the population of potentially infected. Right? But not all of those people are infectable, because in this case you have 90 susceptible out of 100. So this is what he says here is actually the proportion. This is the proportion of infectables. Okay. And this is the rate of transition. Okay. All right. Because what he says is that an infection, if it happens immediately, which is unlike recovery, because recovery takes place at a rate. All right. If you have the disease, a certain proportion recover, and that's what he's calling rate. Okay. So this is sort of an arbitrary way to divide it up, but you can think about this. The way he divides it up is consistent. So again, in this case, population would be the population of proportionally infected or potentially unaffected if you're talking about a different transition. And this is the proportion of the population that is affectable, and then this is the rate of the effect. Right? So you can see how he also applies this to the transition from infected to recovered. All right. So for this transition, for instance, why does he divide it up this way? Well, what happens is a proportion gamma of I is recovered after each day, during each day. And the way he says is that any infected person is potentially recovers. And that's all of them, so that's 1. And then the proportion, and then the rate is gamma. So that's the rate per time, that's the number per day. All right. So that's how he divides that up. So however you want to envision that, this is how he conceptually divides it up. Again, here beta I, that's the number of potentially infectious contacts. This is the proportion of infectious contacts that reach an infectable person. And then if it does reach an infectable person, it's with probability 1. Right? So, and then he draws an arrow here. All right? So those are your rates. Those are your rates of transition. And that's why you have these terms on the right-hand side. And you can see that there's a negative here, because negative means it's the change from S is reducing the S. People are leaving S at this rate. And you have the same term that are entering the I. Now, typically, whenever you have one of these rate terms, you're going to have a negative in one equation and a positive in the other. Same thing here. You have these people leaving and these people coming, right? So there's always this kind of balance. And what that means is, so let me just say that the negative terms balance the positive terms. And what that means is the total population remains unchanged. All right. Now, if you have births and deaths, then that's no longer true. But in many of these epidemic models, you do have the population be constant because it's convenient and has some mathematically nice properties. All right. So this is kind of going, again, still going over from the ground. But this kind of sets us up because we will be constructing these diagrams, and you need to understand how they're constructed. All right, so we introduce a new compartment, exposed. Okay. All right. So what happens is that a susceptible person becomes exposed, and then the exposed person becomes infectable. And we now have a difference between infected and infectable. The important thing about the I component is that someone in the I component can infect somebody else. So this really means or infectious. I shouldn't say infectable. This means infectious. All right. So this is someone who can produce an infection in someone else. So this model draws a distinction between people who have basically been infected but are not infectious and the infectious. So I have been saying that I is infected. Technically, I should say that I represents the infectious. All right. So in this case, we have a transition from S to E to I to R. So let's see if we can understand all these transitions. Okay. New transition will have the same arrow as S to I. Okay. So here we have the same. This is the same as we had before. There's no change here. So the new transition says that, in fact, there's a rate from exposed to infectious. So if you're exposed to the disease, you're not necessarily immediately infectious. And that rate is delta. So what this means is a proportion delta of exposed people become infectious every day. Now you know that there is that exposed to I is something like you have the incubation period. Okay, like COVID has an incubation period of 7 days, something like that. So then this reflects the incubation period. So in fact, the incubation period is 1 over delta. Okay, because the rate is a number per time, and so if you take 1 over a rate, you get a time. So this is the same thing we had here from infectious to recovered. We said the mean infection time was maybe 7 days, and that means gamma was 1 over 7. So roughly 1/7 of infected become recovered at each time period, right? So this delta represents something like the incubation period. So again, we'll be using his variables in our spreadsheet, so we should be consistent with this notation. All right, and here's a new set of equations here. All right, this should not be a surprise. Again, this ds dt means s of n, f is s of n plus 1 minus s of n. And then this s should actually be s of n, right? And then this here should be e of n. All these variables are functions of n. I don't make big N a function of n because big N is constant. All right, so this is going to be e n plus 1 minus e n. Okay, and so on. All right. Now here he talks about programming the exposed component. Now I think that you can do this. You should be able to do this in Excel. So I won't show that right now, but you'll just have to add another column to your Excel spreadsheet. All right. Okay. All right. So here he talks about a model where you have R0 equals 5, and you have a population of 1 million and an incubation period of 5 days. So that means 5 is equal to 1 over gamma. And then recovery takes 7 days. So I'm sorry, that's 1 over delta. 5 is 1 over delta. And 7 is 1 over gamma. All right, so you should be able to program this. And then when I make up the assignment sheet, I will specify exactly how we want to make that happen. All right, so that's where we're going to be headed. Okay, and then you should be able to make a graph like this. We should be able to duplicate this graph in Excel. All right. Now we've got another component called the dead component, because some people who become infected actually don't recover and they die. Okay. So you can imagine where the dead component is going to go. Those who are infected, some of them will recover and some of them will die. So we've got a split now. All right. All right, so let's see how we can handle this transition from infected to dead and read what he says here. Now, I think that what he says is not quite accurate. Here it says, when can people die from the disease? Only while they're infected. This means we'll have to add a transition I to D. Of course, people don't die immediately. We define a new variable rho for the rate at which people die. E.g., when it takes 6 days to die, P will be 1/6. Now, this is really not quite accurate, because if you have a death rate, that doesn't mean that people who are going to die at exactly 6 days. If you know COVID, some people will die in 1 day. Some people might take a week and a half to die. So you don't really want to say this. What you really want to say, this is the exponential rate. Okay. So in fact, rho is the proportion of people who are going to die, the proportion of people who are diable, who die in 1 day. So rho is equal to proportion of at-risk people infected who die. Okay, all right. So for instance, if I have 1,000 infectious people, and then there's the proportion of these who die would be maybe, suppose it's 1 out of 10. So that would mean there would be 100 that die per day. And here it says when it takes 6 days, it turns out that if you have this proportion of 1/10, it takes an average of 6 days to die. So that's the average length of survival. So there's a little bit of inaccuracy there. Right. So he's using his pattern here that, so if we look at this transition, I is the population that death can apply to. And then here we have a question mark. Now, not everybody who's infectious is going to be at risk of dying. So we have to add another quantity here, which expresses the risk of someone becoming diable or someone becoming at risk of dying. And of those people who are at risk of dying, which is some proportion of the infected, then we'll have a proportion of those who actually die. All right, so we have to have some other proportion here. And you have some proportion here, you're going to have 1 minus that same proportion here. Because if we have these, so these people are the at risk. And these people would be the not at risk. Okay, so of the at risk people, you'd have this rate, which is, as it says, the exponential rate of dying, and these are the not at risk, and this is the exponential rate of recovery. So it works the same way. So we need some other variable here, and this is what he calls alpha, which is the death rate. Well, it's actually not the death rate. I'm not sure what he calls it. Let me see what he calls it. Well, he does call it the death rate. I'm not sure this is really accurate, because this is not really the I would not call this the death rate, because it's the I would call it the at-risk rate, because it's not the rate of people dying. Okay, so so this is not quite accurate. I'll call it the diable rate. Diable rate. And as I said, it's the proportion of people who are infected who are at risk of dying. And then you have this average survival rate of those who die, who are at risk of dying. Right? So that makes a complete model here. Whoops, sorry, let's go back. All right, so now we have a more complete set of equations. Okay, and he sets up some more parameters. So he says alpha to 20% and rho to 1/9. Okay, so these are parameters that you can also set. And then you get another model. You should be able to duplicate this. Okay. Now here he added a total because, as I mentioned, the way he has it set up, that the total should always be equal to n. So S plus E plus I plus R should be equal to n. Okay. All right. All right, now here he talks about other components. You might add people who go to ICU. All right. So I think you can see how different components can be added. Right. All right, so here we have time-dependent variables. All right. Now he brings in another wrinkle. To suppose the reproduction number changes over time. So that's something that could certainly happen, and you'd see that that would change these equations here. Well, you'd have to be more specific about how R naught changes. You'd have to change beta and gamma in some way. All right, so let's see how he changes R naught. Does he change R naught by changing beta or gamma or both? Let's see how he does that. So in fact, what he's doing is he's defining beta as R naught times gamma. So here he has gamma is a constant and beta is changing. Okay. So what is beta? According to this here, he has a large value of R naught before L and then a small value. Okay. So here we have a sudden change in R naught. And what that leads to is a sudden change in beta. Okay, so if I wanted to do this mathematically, you would say beta equals, it's going to be 5 times gamma for t less than L, and it's 0.9 times gamma for t greater than L. T greater than or equal to L, okay? Where L is a parameter that he will set. All right? So we can also program this in Excel. Okay, so L is the day where lockdown starts. Okay. All right. So we should actually be able to duplicate this curve in Excel. All right. So he has lockdown after a different number of days. All right. We should be able to duplicate that. All right. Now here he does a variation of that where his R is a continuous function of time. So again, you would have to program beta equals R naught of t times gamma. All right, so he's treating R naught as fundamental and beta as derived from R naught. Okay. All right, so let's see. All right, so of course you can vary this. Remember that beta, all right, so remember that R reflects the number of cases that are produced by a single case. And that's certainly going to be affected by the rate of contact. So here we're looking at different cases of models of R. So for instance, starting out, R is 2. Now, just to give you a perspective, the R for COVID, I believe the R for the Delta variant is something like 5, and the R for the original is something like 2, something like that. So these numbers are quite realistic. So here you're starting out with no lockdown, and then here, for instance, this blue curve is a case where you'd have a sudden and drastic lockdown. This green curve would be a case where people reduce their contacts more gradually. Right? So you can change your parameters in your function to model different practical situations. I think if you passed a law on a certain day for lockdown, you'd have a more sudden change. or if people change their habits over time, you'd have a more gradual change. But here you have the R0 going from 2 down to 1.4. Now 1.4 is still bad. It means that each infection produces 1.4 infections, which is not good. As we've said before, you want your R to be less than 1. Okay. Now he calls this R0. That's really, you really should call it R effective, but that's okay. You understand what he's talking about. It's the reproduction number. Okay. All right, so in this case, let's see what this curve is doing, what we're showing here. So I think this graph here is produced for a R0 change, something like this. He doesn't give all the parameters for this model. All right, well, this starts at 5, goes down to, it seems like it goes down to a 0.5 or something like that. It's not really clear. I don't know if he gives the parameters for this. But when I assign to you, I'll tell you exactly how to set your R0 curve. But in principle, with this information, you should be able to have a R0 curve, and that R0 curve will determine the beta, and then you can use that time-varying beta to implement your model, and you should be able to get curves like this. All right, so in this section, he talks about another approximation of a realistic situation where the fatality rate, like alpha, remember I didn't really call that fatality rate, it's kind of, I called it the diable rate, is not constant and may depend on resources. For instance, if your ICUs are overloaded, then your fatality rate will go up. So the fatality rate may depend on the number of infectious people. So that's what this equation here models, that the fatality rate itself, what he calls a fatality rate, depends on how big what proportion of infectious population there is. So here we say that the fatality rate is some proportionality constant S times the proportion of infectious in the population plus some base fatality rate. Of course, even if there are no other infectious people, some people are going to die. But as I said, if you get overcrowding and you get other factors, then the fatality rate is going to increase. Now, usually, in this case, you wouldn't just have a linear increase. You'd have an increase at an increasing rate. Typically, your ICUs are okay until they get overloaded, and then your fatality rate goes up very suddenly. So this model, this is a gradual increase in fatality rate as the number of infectious increase. But we know that that's not true because, as I said, if you have 100 beds in your ICU, if you're up to 80 infectious people, you're okay. But if you get over 100, then you're screwed. Those people are going to not be able to be treated. Right. But this is also something that we can do on our Excel model. We can make alpha depend on the value of I. So there's really no problem there. We can do this easily. Right. All right, then he talks about age dependency. You may have some, of course, older people are more at risk for COVID than others. So really to do this exactly, you would not have just one diagram here, but two. You'd have one diagram for the younger and one diagram for the older. Now, that's really not so difficult. The difference, however, is that when the transition from susceptible to exposed, well, the people who can infect a susceptible youth could be young or old. So this I here refers not just to the I for young, but the I for the young and old. So it's the combined I. So we would have, we could have S1, E1, I1, D1, R1 for young people, and you'd have S2, E2, I2, D2, R2 for old people. And this rate would depend on I1 plus I2 and not just on I. So we can talk about that. That is not such a difficult thing to do is just adding more columns to your spreadsheet and revising your equations. All right. So I think I'll stop here. And as I said, I will make a more specific instructions on the spreadsheet that you're supposed to make based on these equations. But you will be able to duplicate some of these curves that are in this OneNote. Now, you do have a link to this OneNote. As I said, this is the in your course OneNote, which you can find on Canvas. And the name of the sheet is Infectious Disease Modeling with Excel. So take a look at this, and you'll be making some of these graphs. Okay, that's it.